Next we will look into D edge triggered flip flop. So, it is similar to the JK edge triggered flip flop, but this D edge triggered flip flop can be obtained by connecting the J and K inputs of JK flip flop using an inverter. So, just like that, instead of JK it can be SR also, but it does not matter, but this if you connect an inverter between J and K, then it will behave as a D flip flop. So, it can also be obtained by connecting inverter S and R inputs through an inverter, and the behavior is already behavior is whatever we have said so far, that as long as the clock signal is high or low, or it makes a high to low transition, the Q value does not change. And so, we write it as Q n plus 1, sometimes we write it as Q n plus 1. So, to mean that at the n plus 1th time instant what will happen. So, if we are currently at the nth time instant, so that is Q n, and then at the n plus 1th time instant what will happen. So, to be precise, so you can write it as Q n. Okay. So, to be more precise, instead of writing Q, so you can write Q n. So, otherwise when the clock signal is making a transition from low to high, so depending upon the value of D, it will either become 0 or it will become 1. So, this way we can have this D type edge triggered flip flop. Another flip flop that we get from this JK flip flop is known as the toggle flip flop or T flip flop. So, this T flip flop is simply the JK flip flop when these J and K inputs are tied together. So, they behave like this since this is a JK flip flop internally. So, you see whenever I make this T value equal to 1, then this J and K both of them are getting 1. As a result, whatever was the previous value of Q, so that will be complemented. So, you see here that when this T value is equal to 1, then at the rising edge of the clock, this Q n plus 1 will be equal to Q dash n, to be more precise. So, you can write it as Q dash n. You can write it as Q dash n, whereas if the T value is 0, that means this J and K both of them are getting 0. So, as a result, the value will not change. So, it will remain as Q n, and if the clock is not active, that is it is high, low or making a high to low transition, then also it remains at the previous value. So, this way we can have this T flip flop made. It is a positive edge triggered T flip flop, because the triggering is occurring at the positive edges of the clock. We can, for all the flip flops that we have discussed, so there can be negative edge triggered version also, where at the falling edge. So, we have seen previously how to detect the falling edge of the clock signal. So, when the falling edge is coming, then the signal, the value of the Q will change. So, here when the clock signal is low or high or making a low to high transition, in those cases Q n plus 1 remains equal to Q n. So, the value does not change, whereas if it is making a transition from high to low, then the T value is 0, then this Q n plus 1 will maintain the previous value of Q, that is Q n, and if it is equal to 1, then it will toggle. So, it will change, it will become equal to Q n bar. So, this T flip flop is also a special case of JK flip flop. So, you see that often this JK or SR, it is actually the main flip flop that we design, and from there we can derive this remaining type of flip flops. So, from SR flip flop, so you can come to D or JK flip flop, or you can from the JK you can come to D or T flip flop. So, like that you can get one flip flop from the other. So, some flip flops they come up with some asynchronous inputs which are known as preset or clear. Now, one question, like whenever I am suppose I give you one flip flop, and it is of some type, say D type. Okay. Now, suppose this is say D and this is say Q and Q bar, and if I say if I give D equal to 0, there is a clock, then what is the value of Q? Okay. The answer that we have got so far, it says that the value of Q will be same as its previous value, but what is the previous value of Q? So, that is again dependent on the the time before that. So, that way how long we go back. So, that is we cannot go back infinitely. So, what is done is that there must be a starting point. Okay. So, there must be like if this circuit, if I make a circuit like this and switch on the circuit, then what will happen is that this q and q bar, so they will pick up some arbitrary values, and from that point onwards depending on the d value, so it will go on operating, but the system behavior will become unpredictable. For SR latch we have seen that we should not apply the pattern 1 1, but we do not have any control over that. Okay. So, we somehow want to the q and q bar should always be complementary, that is also said. Now, we do not have any control if we do not have any if we just switch on the circuit and this q and q bar can pick up any value. Now, how can we control it? Okay. So, for that purpose most of these flip flops that we have studied, they come up with two extra controls which are asynchronous in nature. One is known as preset, another is known as clear. So, preset and clear, as long as this they are be 0 0. So, if it is in this particular case, so this is a rising edge triggered JK flip flop. So, if it is for these cases, if it is falling, as long as they are falling edges or the high or low, if this preset and clear both are 0 0, then nothing happens. So, this it continues to the previous value. On the other hand, if this if there is a rising edge like this, if there is a rising edge here from low to high, then this preset and clear, this clear is preset is equal to 0 and clear is equal to 1, then it is this q n plus 1 will be equal to 1. So, that is we can preset this flip flop value to 1. So, irrespective of the value of j and k, so if this preset value is preset control is made equal to 0, then this q output will become equal to 1. Similarly, if this depending upon this preset and clear, if this clear is made 0, so irrespective of the value of this j and k, this q n plus 1 will become equal to 0, the flip flop content will be cleared. So, that is why the names preset and clear. So, irrespective of the values of j and k, if this clock signal comes, the rising edge of the clock signal comes, then this preset and clear will be presetting the value. On the other hand, for the proper operation of the flip flop, this preset and clear both of them should be made equal to 1. So, they are all made equal to 1. So, then you can just when they are made equal to 1. So, then this flip flop operates as a normal JK flip flop. Okay. So, if we read this particular text, it says that two extra inputs are often found on flip flops that either clear or preset the output. These inputs are effective at any time, and that is why they are called asynchronous. If the clear is at logic 0, then the output is forced to 0 irrespective of other normal inputs. If the preset is at logic 0, then the output is forced to 1 irrespective of normal inputs. The preset at and the clear inputs cannot be 0 simultaneously, and so it is a design constraint that they cannot be made 0 simultaneously. So, that is why it is the designer has to, the user has to ensure that I am not making this preset and clear 0 simultaneously, and if both of them are 1, then the flip flop will behave as a normal flip flop. Okay. Otherwise, it will be behaving as per this preset and clear. So, this if the preset signal is 0, then this circuit will be preset, and if the preset signal is, if the clear signal is 0, then the circuit, the flip flop will be cleared. So, that is why it behaves like this. So, we have got another exercise. So, we have got say this D latch, how does it work? So, it is it says complete the timing diagram for D latch, assume that both cases the Q output is initially 0. So, you see that this is D input is high at this point. So, till this much it continues like this, because enable is high, but D is also 0, then it is high, then it will become low, then it will follow that D as long as enable line is, sorry, this is not correct, as long as the enable line is active. So, it will follow the D line, then enable becomes deactive at this point. So, it will continue like this, then enable becomes active at this point again. So, this d value is 0. So, it comes down, then it goes like this, the enable is low, enable is high. So, it continues like this, d value is also low, then enable is low. So, it continues like the enable becomes 1, but the d value is 0. So, it goes like this, enable is 1 and d is 1. So, it becomes high, it goes like this, then enable becomes low, but d is d was high. So, it continues to hold the value like this. Next change can occur only at this point. Okay. So, d is already 1. So, nothing happens, and then at this point enable is going low and d is also going low. So, it will continue like this. So, you can draw the timing diagram for the jk accordingly. So, here this q is 0. Now, this enable is high and j is 1. So, as a result it will become high, it will continue like this. Then at this point k is high. So, it will come low, and then it will be k is again becoming high, j is continuing to be 0. So, after this enable has become 0. So, enable becomes 1 at this point, but at this point j and k both are 0. So, as a result it will continue with the previous value of q, and then at this point j is equal to 1. So, it will rise like this, and then it will be then enable becomes low. So, as a result nothing happens in this part of time, then enable becomes high at this point, okay. And then we have got j and k both are high at this point. Okay. So, it will be making a transition like this and it will continue like this. So, this way we can make the timing diagrams for the this D latch and JK latch. Next, we will look into some circuit changes. So, this diagram also you can continue, I am not doing it. So, you can just draw the timing diagram, fill up this q cube and q output in a similar fashion. This is another example. So, you can I am just putting this slide so that you can just make a few practice. Okay. Now, if we try to there is another type of JK flip flop which is known as master slave JK flip flop. So, the problem with edge triggering was that, so we were requiring some extra edge detection circuit for making it to operate properly. So, if we instead of that, what we can do, we can use two such flip flops, okay, or two such JK flip flops, and the one is called the master flip flop. So, this is the master and this is the master flip flop and this is the slave flip flop. So, master flip flop operates at the when the clock signal is high, and the slave operates when the clock signal is low, because there is an inverter connected like this. So, you see that when the clock signal is high, then this j and k. So, depending upon this value of j and k, this q and q bar will come. Now, during this then the clock signal will become low. When the clock signal becomes low, then whatever values of the values of this j and k, so they cannot change this SR flip flop. So, the previous value will be remaining latched here. Now, this slave flip flop will be following the JK flip, the master flip flop. So, whatever master have done previously, slave will do now. So, this way we can so these two SR latches. So, the flip flop they reads the value of inputs when the clock is 1 and changes the output when the clock is at logic 0. So, here for example, this j and so when the clock signal is high, this q output does not change. Okay. So, this q output will change when the clock signal is low. So, when the clock signal was high, this j was 1 and k was 1. So, it evaluates to 1, and when the clock signal becomes low, at that time the signal makes a transition, it becomes high like this. Now, again at the next time instant. So, by that time when the clock signal was now when the clock signal becomes high, depending upon this j and k. So, j value is low here, k value is also low here. After some time k value becomes active, k value becomes so it becomes to 0. So, this master flip flop becomes equal to 0 at the end of this clock. So, at the end of at this clock boundary when the clock signal becomes low. So, it will be making a transition to low and it will continue like this. So, this way depending upon this clock signal boundaries, so the whatever the master flip flop has made a transition. So, the slave flip flop will make the transition in the when the clock signal becomes low. So, this is the master slave JK flip flop. So, you see that we need a both rising and both level high and level low situation of the clock for the output to get affected. Okay. So, this way with the advantage is that here also we do not have that continuous toggling problem, because for this the slave flip flop will change only when once only during when the clock signal is low, and then only those values will be available to the J and K this first two AND gates. So, these two AND gates the values will be available only in the next clock pulse. So, in between, so previously what was happening is that the feedbacks were coming from these points, okay. But now the feedbacks are coming from the slave. So, the slave will not change immediately when the master changes. So, as a result the master will see the change only in the next clock. So, that continuous toggling problem that we had in the JK flip flop or JK latch that will not happen in the master slave organization. So, this also solves that toggling problem of JK latch. So, we can have this master slave JK flip flop also the same thing, that is you have got this two flip flops and then one flip flop operate on positive edge trigger one edge of the clock and the other. So, this works on the negative edge of the clock and this works at the positive edge of the clock, that slave will operate at the positive edge of the clock, and accordingly the master will read the values coming on the J and K. So, they will be read by the master when the clock signal is in fact, when the clock signal is 0, then the value will be coming here, and when the clock signal is 1, then the value will be outputted by slave. So, here it is written as when the clock is 1. So, in that case this bubble should not be there, and it is written that it is evaluated when the clock is 0. So, in that case this bubble should not be there. So, there is a problem with this diagram and this write up. Anyway, it conveys the basic idea. So, next we will be looking into some conversion, like how can you convert one flip flop to another type of flip flop. That is very common, like maybe while doing the operation. So, we are looking for some type of flip flop, but what we are getting in our laboratory is of a different type. So, we need to do some conversion between the flip flop. The first conversion we will look into is SR to JK flip flop. So, basically we have got an SR flip flop and we want to make a JK flip flop out of that. So, for doing this thing, this type of exercises, first we have to make a conversion table. So, in the conversion table we write down the values of this J, K and the current value of Q, and what is the expected next value of Q. So, these if I take these three as input, J, K and QP. So, these three as input and we see what is the expected value of output. So, from the JK flip flop we know if it is 0 0 0, QP plus 1 is also 0. If it is 0 0 1, so it maintains the previous value. So, this QP plus 1 equal to 1, that is equal to QP. It is 0 1 0, then irrespective of the value of QP, the output is 0. So, QP plus 1 is 0. So, 1 0 0. So, irrespective of if the J input is 1, irrespective of the previous and K input is 0, irrespective of the previous value of QP, the values are 1. And for if J and K both are equal to 1, then if QP was 0, now it will become 1. If QP was 1, now it will become 0. So, if we now we try to mimic this behavior by means of an SR flip flop, that is in SR flip flop we will try to put the values in S and R such that we get this type of behavior. That is, in a flip flop I have got the present state as 0, next state we also want as 0. So, what are the values that we should feed to S and R? and you know that only if I in SR flip flop, if I set this S input to 1, then only output will become equal to 1. So, if I maintain this S input as 0 and irrespective of the R input, it will maintain the value 0 0. So, if R input is 0, then also it will remain 0. If R input is 1, that also will reset the flip flop and take it to 0. Similarly, if the current value is 1 and the next value expected is also 1, then what is to be done? So, you can ignore the value of S. So, you can feed it to, we can feed 1 or 0 to S, but you have to feed a 0 to R. So, as a result, if you set R to 1, then this will change to 0. So, what is restricted is that this R must be equal to 0. So, we should get 1 1 here. Similarly, we should if the current state is 0 and the next, so here also it is same thing. So, here also 0 x 1 0. So, if we want that, if the current value is 1 and the next value we want as 0, then the R input should be made equal to 1 and S input should be made equal to 0. Similarly, 0 1 S input should be made equal to 1 and R input should be made equal to 0. So, in this way we write down the values to be applied on S and R inputs of the flip flop. Now, we make Carnot map that has got the inputs J, K and Q P and the outputs as S and R. So, for the S we make the Carnot map here and for R we make the Carnot map here, and after simplification it turns out that we should make it as J, it is J Q P bar. Okay. So, S equal to J Q P bar and R equal to K Q P. So, if you simplify, so you will get it like this. So, you see that what we have done. So, you have connected two AND gates and this Q P bar line is taken here and connected here and Q P line is taken here and connected here. So, as a result, now this structure it behaves as a JK flip flop. So, in this way if you have got one type of flip flop, so you can very easily convert to another type by putting some additional logic into it. How to do the other side, that is from JK to SR. Okay. For JK to SR, so the ultimate behavior expected of the SR flip flop is like this, that it is 0 0. If it is 0 0, then if the S and R are 0 and Q P is also 0, then Q P plus 1 should be equal to 0. If it is 0 0 and 1, then Q P plus 1 should be 1, that is it is holding the previous value. If it is 0 1, then this Q P whatever be the value, Q P plus 1 will be equal to 0. Similarly, 1 0, whatever be the value of Q P, output be equal to 1. And for SR flip flop or SR latch, we do not apply this 1 1. So, these two are not put. So, for JK, so we can simply consider them as do not cares. Now, if we want to get this behavior, that is what value should be applied to J and K such that we get this behavior, that is if Q P is 0, Q P plus 1 is also 0. So, here also if you put J equal to 0, if J equal to 1, then this Q P plus 1 will become equal to 1. So, we have to make J equal to 0, K is a do not care. Similarly, 1 1, so K should be equal to 0 and J is do not care. Similarly, 0 0, again the same thing, J is 0 and K is do not care. So, in this way you can fill up this J and K part, and then you can do a truth table Carnot map and try to simplify this Carnot map, and then what you get is J equal to S and K equal to R. So, you do not need any additional gate to convert one JK flip flop to SR flip flop, and that is quite expected, because that is the we have seen previously also the behavior of JK and SR, and we have seen that they work exactly like that, JK and SR. Only thing is that in SR this 1 1 input pattern will come, that is not there in the JK. So, we are not bothered about the 1 1 input pattern for JK. Next, we will be looking into the technique how to convert a JK flip flop to a D flip flop. The strategy is similar. So, for the first we write down the table for the D flip flop. In the D flip flop, if D input is 0 and Q P is 0, so we want that Q P plus 1 should be equal to 0. If it is D is 0 and Q P is 1, then also it is 0. D is 1 and Q P is 0. So, this Q P plus 1 should be equal to 1. So, this is the D flip flop behavior. Now, if we want to realize this behavior by means of an JK flip flop, then what we have to do is, so I have to apply a 0 at j, because to get a this k input can be do not care, then it can be the, if since the QP is 0, it will always come to 0. Similarly, so if we are looking for if the previous value of QP was equal to 1 and we are trying to get a 0 here, then this k value must be set equal to 1, then it will be resetting it to 0. Similarly, if the previous value of QP was 0 and the next value is 1, so we have to set this j value to be equal to 1, so that it makes a transition from 0 to 1. And from 1 to 0, again this x and this k value, so since the d input is 1, so this is 1 to this sorry, this is the d input is 0, previous value of QP is also is 1. So, I have to make this way. So, then if we do a simplification of this corresponding k map, so it will turn out that between j and k, so j is equal to d and k equal to d bar. So, previously I have said that while making the d flip flop, that you have to connect an inverter between j and k input. So, this particular derivation shows that you can do that is really the case, that you have to connect an inverter between j and k. So, can we convert a d flip flop to a jk flip flop? Okay. So, how can we do this? Now, you see that this is a bit cumbersome, because this jk, so we have got this truth table like jk 0 0 0, then the expected. So, this is the expected behavior. Now, we try to note down what should be the d value, like from 0 I want to go to 0. So, d input should be 0, 1 to 1. So, that should be 1, 0 to 0 0, 1 to 0 0, 0 to 1. So, I need to put a value 1. So, that way I write down this d input column. Now, we make a truth table out of j, k and qp for the d, and if you do a simplification, then you can find that it turns out to be a function d equal to j qp bar plus k bar qp. So, if you are given this so at this from this j and k, we have to derive these two this function for d. Okay. So, j qp bar, so qp bar is taken, it is ANDed, and k bar qp, the qp is taken, k is inverted and ANDed, and they are ORed here and then put to d. So, this logic, so this will be converting one d flip flop into a jk flip flop. So, internally it remains a jk flip flop, but sorry, internally it remains a d flip flop, but we can realize a jk flip flop out of that.